All right, so next in terms of two-dimensional waves, we're going to look at a different phenomenon that waves can actually do. And here we have a nice little simulation. We've got like a wave generator on the left, and we've got like a, you can think of like water. It doesn't make any difference. Pool of water, and we've got like a wall with a hole in it. And the waves are going to come in from the left. There we go. Nice big flat waves are coming in. And they are going to go through that little opening and through the barrier. Now, what's going to happen when the waves go through the hole? Now, we know when the waves hit the barrier, they'll reflect back. But what about the waves that go through the hole? Well, let's see what happens. As the waves go through the hole, they sort of round out and spread out as they keep on going. Now, this is what's called diffraction. When waves will go through an opening, they will spread out. And there's reasons behind this that we'll get to later on, but they go through openings like this and they will spread out. And this is what's called diffraction, and this we're going to look at a little bit next. So this is what we're talking about. So we're looking at what's called diffraction. And basically in diffraction is when waves actually go through some kind of opening, and when they go through an opening, they will actually spread out. That's what waves do. So, for example, so like we sort of sketch what we had over there. We got something like this. We got a little barrier, and we had our waves coming in. So there's our waves, something like this, and they come through here, and they will start to spread out. Okay, and that's what diffraction is. And this is why if you go, if there's somebody talking in a room and you go past the doorway and you're outside, you can hear them when you're not necessarily perfectly in line with the door, because the sound will go through an opening, whether there's somebody talking or music or whatever. It'll go through the opening and it'll actually spread out. Okay, but how much it spreads out and how well it spreads out, that sort of depends a little bit on the situation. If you actually take some measurements, obviously, these guys, the waves have a wavelength, and we'll just call this opening D, the distance for the opening. The best diffraction occurs when those two are about the same size. If you want the best diffraction possible, you want the wavelength and that distance opening to be about the same. They don't have to be exactly the same, but approximately equal to each other. You want them to be about the same size. And I'll sort of show you what happens if they're not the same size. So if you go back to our simulation, right now it is set up where the opening and the waves are about the same size. This size here, and this is like a crest, and the black part's a trough, that distance and that distance are about the same size. So this is right now set up for really, really good diffraction. So what happens if I make the opening too small? If I start taking that opening and I make it really, 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 really small compared to the size of the wave, it's still spreading out, but I don't know if you can sort of tell that it's gotten fainter. So much energy is being blocked, so much of the wave is being blocked and just reflected on the opposite side, you don't really get good diffraction. It's spreading out, but it's really, really, really weak. Now, if we go back to match them up, you can see how much darker and brighter it gets. Like it just works way better. Now, what happens if the opening gets bigger? Well, if the opening gets bigger, and that's as big as I can make it in the simulation, you can sort of, hopefully you can kind of tell that the middle part that's going through isn't as round as it used to be. It starts to flatten out. Here, I'll make the opening a little smaller again. Okay, something like that. And if you look especially in the middle part, it's nice and it's pretty round, especially about halfway it's gotten nice and round. But if I make the opening bigger again, it stays a lot flatter in the middle for quite a bit longer, and it doesn't get quite as round as quite as quick. And if it's not as round, it's not going to spread out as well. Okay, so those are the effects of when the opening is too big or too small. So if we go to this, back to this picture here, if that D value is too small, okay, basically too much of the actual wavelengths and stuff like that is blocked. Okay, so there's not enough really of the wavelength and the energy going through. Too much is blocked, and it's really, really, really weak. So this makes it very, very, very weak. If the D value is too big, lots of energy gets through. That's no problem, but it's not as round as it was before. so there's going to be less spreading. And the whole point of diffraction is for the waves to actually spread apart. So you just got to keep in mind that's not just about how big the opening is, it's how big it is compared to the wavelength. So if you've got a really small wave and a really big opening, its tons is going to get through, but it's not going to spread out very much. It's going to go relatively straightish through. And if you have a really small opening and a big wavelength, then just too much gets, it's round, it's really round, but so much of it gets blocked. And this is basic diffraction. So this is why if you have like music playing in a room or something like that, and it's part of a much bigger building or something like that, you'll hear the lower waves outside the doorway a lot bigger area, because the longer, bigger wavelengths will spread out more, where if you want to hear like the higher tones, you sort of have to be in line with the doorway, because they're not going to spread out too much and not as good, kind of more flatter out through the opening because they're way too small compared to the wavelength. So remember, it's not just the size of the wave, it's not just the size of the opening, it's the comparison between the two. Okay? All right, well, let me show you something else involved with round waves and stuff like that. That's kind of a common thing when you have different types of waves. Except instead of one source of waves, we're going to look at two sources of waves. Okay, so let's go back to another one of these little simulations, because it's almost impossible to try and describe it. It's a lot easier to show what we're going to do next. So think about this as a body of water, and we've got a couple faucets here. I'm just going to turn one on and just put some drops of water there. There's our nice little drips of water making our nice circular waves as they go around. And I can do the exact same thing with my other source of water over here. I can have that one make droplets too. Okay, but what we want to do is, instead of just having one wave source, we are going to have two wave sources that are going at the exact same time. And when we do that, we get what looks like this. Okay, and the waves are interfering with each other. You guys have looked at constructive and destructive interference before in one dimension, but this is in two dimensions. And this is what's called an interference pattern. Okay, I'm just going to pause it a little bit before you get hypnotized. So you guys know that when waves travel and they meet other waves, they go through each other. They don't actually affect each other, but they can build and have constructive interference and have a higher amplitude. They can also have destructive amplitude or destructive interference where you get a lower amplitude. And that's exactly what's happening here. And you get sort of like this fan pattern going on with these like simulated water droplets. Okay, so we're going to look at this a little bit and sort of see how this works, what we can do with it. All right, so using the amazing powers of modern technology, took a little screenshot of what we were talking about before, and we are going to look at what are called two-source oops, get rid of that over there. Two-source interference. Okay, I'll sort of show you how this works. Now, this is straight from that simulation I showed you before, when we got like two sources of waves and they give a little fan pattern. Now, to give you an idea what this more accurately would look like in real life, I'm going to show you a different viewpoint from a different little video that I have. So this is the same type of thing. We got our two source at the top, we got the fan pattern, but what's nice about this one is once it goes, it'll actually give it from an actual perspective. So if you see, we've got the two sources way back there, and we got this fan pattern of waves. Now, if you want to think about water waves, so if these are water waves, if you're riding in these ridged areas, bumpy areas, you're bobbing up and down, but there's areas where there's water is actually perfectly still in between, and you get these bands of maximums and minimums in the actual medium, whether it's water or whatever you want. Most people just think about water when you're looking at this type of stuff. Okay, and this is what we're going to look at a little bit today. Okay, and this is what's called two-source interference. So in two-source interference, we've got this sort of like a little fan pattern. We've got different areas where there's big waves and small waves. Now, if we sort of analyze this a little bit, I'm going to move this down just a little bit more. Okay, there we go. There's different areas. Now, this part right here, here we have maximum waves. They're really big and ripply. Always in the middle is nice and big and ripply. And same thing here. We've got a maximum there. We've got a maximum there. And that's where we have really, really high waves. So this is where we have a really, really high amplitude. And these are often called antinodes. So where you have maximum amplitude, that's called an antinode, and I got 3 labeled on here. And right in between, like right here, that's a minimum. Same as right there, we have a minimum. And here, the amplitude is technically equal to 0. There's like no waves, and this is often what's called a node. So you get a series of maximums and minimums, a series of nodes and antinodes from the two sources that's very symmetrical. Like our two sources are perfectly identical, they're synchronized the whole bit, otherwise the pattern can actually shift and bend. This is idealized. So nice and symmetrical pattern works really, really well. And actually by affecting the frequency and different things, you can actually change the pattern. So if I go back to this one, if I actually take the waves and I make the waves bigger, it actually changes the pattern. It actually makes it much wider and broader. Okay? By increasing the frequency, which lowers the wavelength, it becomes a little bit more intricate. Okay? I can also change the distance apart from between the two little taps. If I move them really, really, really close together, the pattern actually becomes broader, a little bit wider. And if I take those and I move them as far apart as I can, you will get smaller, finer pattern out of it. So it all depends on the geometry and the situation, how things are actually laid out. It depends on lots of different things. Okay, and we'll look at some of those effects and factors and a little bit later on when we take some more detail on another phenomenon. But anyway, let's look at how we can figure out, depending on where you are you at a maximum or a minimum, depending on where you are. So I want to show you how you can actually figure that out. Okay, so I'm going to take a point. I'm going to take a point right here, and that is a maximum right there. That is a maximum. If I look at where I am, if I actually analyze it based on my sources, and the sources are actually right there and right there where they're actually hitting. If I actually took some measurements and I measured the distance from here to here, and I measured the distance from here to here, not in meters, but in wavelengths, I would find that I'm exactly 1 or 2 or 3 wavelengths farther away from the other. Okay, now this may seem kind of weird, but that's the way this works. If I actually look at where I am positioned on here, if this is 3 wavelengths, that's probably 5 or 6 wavelengths, maybe 4 wavelengths away. So I want to show you how this works. Basically what you want to do, if you want to find out if you're maximum or minimum, well, that depends on one very important thing. Are the wavelengths synchronized? Because you want to know if here's one wave where you're located, from one source comes like this. If the other source is like this, the waves are perfectly matching, these two are going to build up and give you a really high wave. Those two are going to give you a really low wave. If that's not the situation, if one wave is like this and the other wave is like this at your location from the two sources, these guys are going to cancel out, these guys are going to cancel out, and you're going to get nothing at all. And that is what's happening in different locations. At this maximum right here, you've got waves from two sources, and those two waves are perfectly matched up to give you really, really high crests and really, really low troughs. If I go to a different place, if I would go, say, right here, that is a minimum area, definitely a minimum. And if I would measure those two distances like this to that location, and I could see the waves at that location, they're not working very well. One wave might look like this, and the other one might look like this, and that's why they're canceling off. So it's all about how well the waves are synchronized with each other. What you want to know, do the crests match up? Let's fix that. Are the crests matching? Because that would give you a maximum. Or do they don't match? That's what we're looking at. Are you in crest on crest, or are you in crest on trough from those two sources? Because that's what's going to dictate whether or not you're going to have a high wave or a low wave. Okay, so it's all about not positioning from one source, it's your positioning from both sources. At your location, what kind of wave are you getting from one place? What's the wave you're getting from their place? And how well those two waves overlap. Okay, so we'll be looking at that type of thing next.